Yeah, thank you. It's a pleasure to be here. Thank you for persevering till now. My talk is going to touch on a few of the things that have already been said, but I'm going to diminish those things that you've seen 3 or 4 times already today, and we may end a little early as a result. But I just wanted to reemphasize the interesting nature of searching for intermediate mass black holes and the tidal disruptions that might occur near them, and perhaps, as we heard, the connection to white dwarf disruption and the connection to fleshing out black hole demographics at the low mass part of the distribution. And to do that, you really want to start selecting samples of perhaps dwarf post-starburst galaxies. Now, we may argue, especially from what we just heard, that that would end up being a potentially biased sample, but we have to start somewhere, and we want to be efficient. So it's good to ask whether or not you can find tidal disruption events associated with dwarf post-starburst galaxies. So does anyone recognize this dwarf post-starburst galaxy we selected from the Sloan catalog? This is a legacy survey image. It's okay. I know you're tired and you may not have all of them memorized. But this was a selection of a dwarf post-starburst galaxy, which serendipitously recovered anybody recognize it now? This is Assassin 14Li's host galaxy. And we didn't know that before we started searching. So that was a bit inspirational. It was particularly interesting because it was one out of, as it turns out, about 190 dwarf post-starburst galaxies we've found now by pushing harder in the Sloan survey. And that's 1 out of 190 compared to 1 out of about 1,000 for giant post-starburst galaxy hosts. The statistics are terrible. They're going to get better. I will make no further claims, but it's curious. So to me, the most fascinating aspect of tidal disruption events favoring post-starburst galaxies, at least if they're optical or X-ray tidal disruption events, and I guess the jury's still out about infrared tidal disruption events, but that fascinating element of this still unexplained connection to galaxies that have had this very strange star formation history, that are often seen as being post-merger galaxies. And what is going on in the nucleus is fascinating, because what's going on in the nucleus is on parsec, subparsec scales. And we are talking about the global characteristics of a galaxy on kiloparsec scales. And somehow that tidal disruption event seems to know to happen in these galaxies. And it's very reminiscent to me of the famous or infamous black hole stellar mass relation or bulge mass relation in galaxies, and all the interesting speculation and theorizing that came about as a result of this connection across this wide range of scales that was unexplained. In the type of work we've been doing in post-starburst galaxies for many years, and I had done it for many years before I even knew tidal disruption events were involved. That was kind of how I got involved in this. Those surveys tend to be dominated by giant post-starburst galaxies, and dwarf post-starbursts are important for some of the reasons we've already heard. From the galaxy evolution perspective, if you find a dwarf post-starburst galaxy, it may have arisen from a dwarf-dwarf merger. Those are very interesting and poorly studied things in galaxy evolution. You might imagine they don't happen very much. Dwarfs are small. They tend to miss each other when they fly by, but there are a lot of them. And we'd like to learn more about that. And they could be intermediate mass black hole hosts. They might even be the sites of white dwarf tidal disruption events. And there's kind of a very unexplored connection to QPEs, in which QPEs to date have been mostly found in dwarf galaxies. That does not mean they only occur in dwarf galaxies. They've been detected nearby where the signal to noise is high, and dwarf galaxies can be detected nearby as well, and there are a lot of them. So We don't know about that, but if QPEs are connected to TDEs, then QPEs are connected to post-starburst galaxies and maybe connected to dwarf post-starburst galaxies. So if you can follow the logic of all that at 5 o'clock in the afternoon, good for you. All right, so some of the questions that, and a few of which were already raised by Yair and some of our other speakers earlier, was what host do tidal disruption events prefer? Again, if you're an optical and X-ray tidal disruption event, you seem to prefer a post-starburst galaxy. I'm not going to go over all that again. What's so special, though, about post-starburst galaxies? I'm going to tell you a little bit about that in case you don't know. I think they're very special, but there are reasons. Post-starburst phase or evolutionary sequence, this actually relates to the point, that very interesting discussion that we just had about the infrared and infrared tidal disruption events. Are there tidal disruption events that occur in a lot of other types of galaxies? Are there tidal disruption events that don't just occur at the post-starburst phase of evolution, but occur before and after that phase of evolution, just prior to the merger, during the merger, while the starburst is active, or after the galaxy settles down and becomes quiescent? To date, we haven't seen a lot of those. And what is it then that's special about that moment in that evolutionary sequence that is the post-starburst phase that only lasts for, of order, the lifetime of an A star? Why do TDEs favor post-starburst galaxies? Yair raised this question. I'm not going to give you any answers to it. I'm just going to re-raise it and connect it to dwarf post-starburst. But lastly, you know, can dwarf post-starburst connect us to tidal disruption events and intermediate mass black holes, and interesting tidal disruption events, like white dwarf tidal disruption events? All right, well, here he is again. That's Yair. It's the first time I met Yair is when he was giving a talk at NYU, and he showed this plot, and I gasped because I had been working on post-starburst galaxies for some time, and he mentioned that he was seeing a lot of these optical tidal disruption events in these galaxies, and we got to talking, and we got to collaborating as a result of that. But in case you don't know, the reason a galaxy evolution person would look at these spectra and gasp is because, unlike many other galaxies, they have very strong Balmer absorption lines, which indicate that they've recently formed stars, but they do not have nebular emission lines, which indicates they are not currently forming stars. And since the name of the game in galaxy evolution is try to understand why one type of galaxy is different from another type of galaxy, and you see evidence in the spectrum for a transition, you get intrigued and you want to explain it. That's a post-starburst galaxy. Yeah, you've seen all this. Decker, brilliant work. It's about 30 times to 150 times enhanced. Okay. What's so special about post-starburst galaxies? So this was this cartoon sequence that I mentioned before, where the post-starburst phase of evolution could be a single frame in this evolutionary path. So you have two disky, gassy galaxies merge. Again, this doesn't have to happen in every case. There are variants. But in general, the idea is you merge two galaxies, they go splat, they create a burst of star formation. They may have a tremendous amount of winds generated as a result. We have lots of evidence for that. You enter the post-starburst phase where the star formation ends, and you end up with a quiescent galaxy. I think, Decker, you made this plot long ago, and I stole it. Thank you. Okay. So for some reason, this is where we've seen optical and X-ray tidal disruption events. We haven't seen them here. Maybe things are too dusty. We haven't seen them here where it should be easy to see them. Not yet. So what are some of the things we know about post-starburst galaxies in general before I get to the little ones? We know that every bit of evidence, observational evidence that we've been gathering to date and simulations suggest that this sequence is a viable path to this phase. We look at morphologies, stellar evolution, gas evolution, dust evolution, color gradients in galaxies with modeling. This is consistent with ending up at that phase. So the formation of these objects through gas-rich mergers in many cases is fairly established. There's lots of tidal features that have been observed in these objects. Do they become red, dead type galaxies? Again, when you look at their star cluster populations, when you look at the evolution of the color gradients and the stellar populations, when you look at the fundamental plane, when you look at every conceivable observational measure of galaxies that we know about, these galaxies do appear to be in transition and do appear to be pointing to ending up in this phase. I'm skipping over 3 talks worth of material, but I'd love to talk more about any of these statements. But that's kind of our consensus at this point. But you can ask why it is that the starburst ends and gives you a post-starburst phase. And that's a good question. We're still picking away at that, but work by Decker and others really suggests that there's not enough dense gas in this phase to have star formation. And it's possible that that gas gets pumped up or energized in some way by outflows to prevent that from happening. With regard to this question about whether or not it's this phase versus this sequence where tidal disruption events occur, I think it's a deeply interesting one. I can show you a plot that Decker made some time ago. If you just focus on the x-axis and you look at the time since the starburst ended in a post-starburst galaxy, and you look at the contours, which is the space of post-starburst galaxies in the Sloan Digital Sky Survey, and then you look at what is now a few data points, and Decker tells me more are coming, you can see that the tidal disruption event host galaxies tend to lie where the Sloan post-starburst galaxies do, along the axis of the age since the starburst ended. What's interesting about that is within the post-starburst phase, there's no pile up at early times or a specific time. It seems that they're distributed much as galaxies that are not obvious hosts of tidal disruption events are. And I would mention this to speak to the last talk with regard, and I think it's a bit of a mystery in my mind in the last few minutes, is we know, again, from Decker's work and Zhou Li's work, that the dust content of post-starburst galaxies decreases pretty dramatically over this period. So if dust were obscuring tidal disruption events, we might expect to see them displaced relative to normal post-starburst galaxies at relatively late times when the dust content has dropped and starts to approach something that we see in quiescent red dead galaxies. We don't see that. That's been a bit of a mystery. But it points to this idea that maybe dust, at least for these, is not controlling when we see them. And it's the phase that's important. Okay, and as Yair mentioned, there are lots of reasons as to why this preference exists. I don't think we've nailed any of them. I've had check marks and X's and question marks flipping around and on this plot for a long time. Whenever a new paper comes out, I think, okay, I can scale that question mark up to a check mark. But we're not quite there yet, I think, in any of these categories. Yair mentioned today he really, really wants this to be true. We'll see. I think it's a great idea that unusual orbits from a galaxy-galaxy merger might be created. These anisotropies might actually up the tidal disruption rate in post-starburst galaxies. And I think we've certainly seen evidence that post-starburst galaxies tend to have central stellar concentrations. And, you know, depending upon that Osterreicher Stone paper that you showed earlier and how valid its assumptions are, you know, we may have to square that with the fact that these are particularly centrally concentrated objects. which would seem to suggest that tidal disruption events could be more common there. There are also gas-concentrated objects, and that may play a role as well, and is probably worth thinking about. All right, well, let me move on to dwarf post-starburst galaxies. And I think some of the questions that we would like to answer, and that I'm going to show you extraordinarily preliminary results about literally in the last 2 weeks we put this together. So we'd like to know if tidal disruption events are more or less common in dwarf post-starburst. So is there a variation in the rate of post-starburst galaxies as a function of black hole mass? We'd all like to see that plot. Are dwarf post-starburst galaxies post-merger like their giant counterparts? Are there central star clusters? There's a history of detecting bright blue cores in post-starburst galaxies. What do the dwarfs look like? Are there AGN present? Could we, going back to Yair's theory of the day, perhaps look for double nuclei in these as a result of the merger and maybe related to intermediate mass black hole binaries? Okay, my student Yang Sun has done some great work on this. You can start hunting dwarf post-starburst galaxies by basically lowering your standards and going to lower signal to noise and objects that Decker would have thrown out from her survey and did to try to find the less massive ones. So if you seek below stellar masses of 10 to the 9.5, and you assume, and it is an assumption for a lot of the reasons mentioned earlier today, a black hole stellar mass relation, that turns into a black hole mass distribution, where you could expect intermediate mass black holes down to the 10 to the 4th in this sample. That's the serendipitously recovered host of Assassin 14Li with our sort of blinded dwarf post-starburst selection criteria. And as I mentioned before, a much higher fraction of these galaxies based on this one object. But we need to push on that quite a bit more. There could be a redshift bias to this apparent preference for dwarfs. These are also dwarf post-starburst galaxies. At least 5% of the sample have these really dramatic, very easy to see features. At least 15% have some visual disturbance, not quite as dramatic as this. A higher fraction have sort of a quantitative asymmetry. So they are messed up in their way, and there is evidence here that dwarfs can merge and make post-starburst galaxies. Student Jung-Young Jeff Kim has actually written code to fit surface brightness profiles to all the galaxies in the Sloan survey. I asked him to focus on these dwarf post-starbursts and post-starbursts generally, and he's done an amazing job. So he actually has found examples where there are point sources in the centers of these dwarf post-starburst galaxies that are inconsistent with bulges. So bulges tend to be a half a kiloparsec or larger. These are considerably smaller than that, even though they're unresolved. If you take a look at one of those sources in the BPT plane, one of those dwarf post-starbursts with a nuclear source, the only one where we have BPT features, you can see that it occupies the AGN territory. And then the last thing that I'd like to show you is one of the dwarf post-starbursts that Jeff has been analyzing. And what you can see here is the relative fits and the residuals between fitting a Sirsic profile and a single point source and a double point source. In the double point source model, the two nuclear point sources are separated by about 70 parsecs in projection. So that is really worth following up. He literally just got that yesterday. All right, so I asked these questions at the beginning of the talk, and I'll kind of answer some of them, hopefully to stimulate more conversations with you all. Lots of evidence for post-starburst galaxies being favorite sites for tidal disruption events, at least optical and X-ray tidal disruption events. Lots of evidence, which I didn't really get into, that post-starburst galaxies form from gassy-disky galaxy mergers and transforming into quiescent, bulgy end products that don't have dense gas and therefore don't form stars. There's some evidence that this is a special phase and that dust does not interfere with one's ability to detect tidal disruption events earlier in the phase. And this question, I think we should all be thinking about, is why tidal disruption events favor post-starburst galaxies. There's some evidence to point to each of the theories that I briefly put up there, but I think nothing is definitive yet. But finally, with regard to dwarf post-starburst galaxies and our very preliminary results, we have a sample in which we could potentially sample down to 10 to the 4, 10 to the 5th solar mass, intermediate mass black holes. We recover the 14 Li host. We weren't expecting to do that a priori. We see evidence for tidal features. These are dwarf-dwarf mergers some of the time, but these central point sources are quite intriguing, particularly one that seems to lie in a host consistent with an AGN, and this latest one. And I should say all of these numbers, they're preliminary in the sense that they're lower limits. Jeff has just gotten the code to work to our satisfaction and is just starting to go through it, and he's finding some very interesting things. So I'd love to talk more about it, and thank you very much.
In general, dwarfs have much burstier star formation histories than massive galaxies, so one might think that the selection of post-starbursts is picking out something rather different. So I just wondered what your perspective on that is.
I completely agree that you may just get lucky in the moment with some of these objects. And so what we're doing now is we're following them up in the same way we've classically followed up their giant counterparts, and actually looking at the morphology and the stellar kinematics and the color profiles in the stellar populations in a way that should address some of your concern.
Well, specifically, that'll specifically get at then, I guess, the question of whether there is a merger sequence or anything like that.
Right.
My guess would be that most of the low mass post-starburst population is physically rather different from the higher mass.
Yeah, so I think, you know, it's harder to see some of these tidal features, but they are close by, and the fact that we are not at the 50% level, which we typically are when we look at giants, may indicate that these kind of major mergers are less common, and that burstiness, you said, whatever is driving it, is putting some very different galaxies into the sample, and I think we do have to address that.
Interesting.
Yes, absolutely.
TDEs. Yeah, exactly.
Good point. Yeah.
I had a question on some of that last exciting work that your students are working on. I guess, what redshifts are the samples at, and what sort of size scales do you think you'd be able to resolve with this code?
Yeah, so in this case, we're looking within 0.04 in redshift.
Okay.
And so I think you don't, I mean, I don't have the plot with me, but if you look at a plot of what the central source would be in physical units as a function of redshift, you get below about half a kiloparsec at around 0.04.
Right,
so.
Okay, that's kind of what I was thinking. Yeah, thanks.
When you say that some dwarf post-starbursts are visually disturbed, what are you looking at and how are you quantifying that?
Yeah, great question. So the ones I showed you were kind of the you know, you look at them and there are tidal disruptions, but you're seeking something that you could potentially compare to simulations or at least reproduce among observers. And what one of the things that Yang Sun has been experimenting with is the various asymmetry definitions that are in the literature. So there are various ways in which you can flip the galaxy and subtract it and look at the residual, for example. All sorts of symmetry versus asymmetry measures, what fraction of the light is in the asymmetric component versus light component. She's in the process of calculating that for these galaxies. So we're not just saying, hey, look at the tidal feature.
Thanks for the great talk. I think I'm one of the people that's guilty of poo-pooing these supermassive black holes. But it may be a misunderstanding on my part. We wrote this paper with Nick arguing that it takes a lot of fine-tuning to get the delay time distribution to work, and you don't have enough events. But I guess it's my own ignorance, because I guess the issue that we found was there's sort of two processes. When a galaxy merges, you flush gas to the center, but then you also have the black hole, which is going in on its own time scale that doesn't know about that. So why are these two things like happening simultaneously? If that's really what's going on, maybe I'm missing something. But it seems to me it's not just a matter of you have to understand why the black holes would be coming in. Of course, it's also probably related to whether we'll ever see any counterparts to LISA black holes.
Yes, I completely agree with you, and I don't think we've seen strong evidence to support the theory as you're suggesting.
But you are saying now maybe you have a candidate.
I'm saying, gee whiz,
okay.
We have at least one candidate that is intriguing that we need to follow up. But we don't know that that's a tidal disruption event host. I'm showing you a dwarf post-starburst sample, and if we see enough of those, disproportionate number of those, and we start connecting tidal disruption events to these dwarf post-starbursts, then I think it will be a more complete picture, but we're going to have to wait a while for that. I think there will be a lot more. I mean, we have about 190 of these systems from Sloan, but by the time DESI comes out, I mean, and it's going to be so much deeper, we're going to have quite a few more to work with. And that, combined with LSST and Ultrasat and everything people have mentioned, should really give us a much firmer basis for studying these things.
Okay, any last thoughts? If not, let's thank Anne and all the speakers today.